So, hello and welcome back to my C++ tutorial playlist. In this video, I want to cover how to do client and server communication in C++, and I thought let's use this as an excuse to write our own custom C2 framework. And first of all, what is a C2 framework? I've written a really bad one in the past in Rust, and that is called appropriately Ghetto C2. But we can take a look at how that worked so we get an idea of what a C2 framework allows us to do. The whole idea is that we want to have remote control over some other device. As we can see here, we have our attacker, and then we have a C2 server that basically keeps the sessions open to the clients. And the clients here, we usually don't have an open port, so we can't connect to it, but instead we connect from the clients back to our C2 server, and that is how we go about it. And why don't we have a direct connection? Basically, this is also an end user device usually, so we don't want to have that running all the time. Instead, we have a server running all the time that gets all the updates from the client all the time. Basically, a command can be sent from the C2 server to establish a remote shell to an SSH server, but that was just the old C2. So, and also this is a very simple GUI where we can send commands to the C2 server that will then be sent to the clients. Now that we have a basic idea of what a C2 framework actually is, let's take a look at how we could build our own. And the one we will build is called Malware. I quite liked the logo and the name. Initially, I thought I would use it for a game engine, but now I'm using it for this. So, okay, where do we start? Let's start out very simple. So what we want to have is, of course, we have a C2 server, and both the attacker and the victim will connect to that. And probably we don't want to have the attacker and the victim access the same endpoint. We might even think about having a relay for the victim, a relay server, so it doesn't connect to our C2 server directly, but for simplicity, let's just use two different APIs, one where the attacker can connect to and one where the victim can connect to. But how do we establish the connection? There are many ways how we can establish connections. For example, we could tunnel them through DNS because that's often overlooked, and there's a interesting proof of concept of that on GitHub called DNSCat and DNSCat 2. Same applies for ICMP packets. These are usually just ping packets, so they are often not looked at by SOC analysts, but these techniques are also very widely known now, so that might have changed. Then you might want to use WebSockets to establish a connection, or even RDP or other protocols, other application protocols. We could also, of course, use plain TCP connections and build our own custom protocols on top of that, but that might look very suspicious to even automatic analysis done on the network traffic, so that might be something we want to avoid. For a real C2, you would want to tailor that to your needs and really have a look at the target and take a look at the target network to understand what traffic is usual there and how you can blend in there. For example, it might make sense to hide C2 communication, for example, with steganography in images, and for example, upload those to an image board or download commands from an image board as an image. That might look okay for end user devices and desktop devices and so on, but it might look very off if we infect a server that, for example, then accesses Instagram or something. So just keep that in mind, that it really depends on your environment. Or a really common method is to use HTTPS because everyone uses it. Our browsers speak it all the time, so it might blend in very well. So that was the whole idea, and it's also common and simple, so let's do that. So how that will look like then is we have two web APIs, both speaking HTTPS. And on the one hand side, we have the attacker API, which the attacker can connect to send commands to the C2 server and also get results or fetch all the things he needs from the C2 server. And also on the other hand, we then have the victim PC that can use the victim API to send its beacons to and also get responses with the commands back. So that will look like that. And what is beaconing? Beacons are just usually small packets. We want to keep them very small with basic information about the client, and they are sent in time intervals and in a loop to the C2 server. And in the response, we get a list of commands for the client to execute. So these are just heartbeats, for example. So the C2 server knows that the client is alive and also tells some basic information about the client and how one packet might look like. I've decided to use JSON for the beacon, and we can see here we have the whole packet. And in there we can see the beacon with the host name and the internal IP, the external IP, then the operating system, and also the user that is currently logged in. And it might also contain an array of results for the commands that were issued to the client. And the commands I want to support for our C2 are these ones. I kept it very small and simple. So with sleep, we want to stop the implant on the client from doing anything for a certain duration. So we can, for example, if we know that there is extensive network auditing in a certain time period, we can pause our operation, for example, and send a last command to the implant so it will pause for a certain time duration. Then we will also be able to open a reverse shell to the client so we can remote control our client. We can remote control the device of the victim. And also we want to be able to close open shells again, open shell sessions. And they are limited to a port. So that is a perfect identifier for our shell sessions. So the C2 server spins up a listening port that can be used to identify shell sessions. Then also we want to be able to take screenshots, and that will then get sent back to us in the beacon. Also, same applies to the loot command that will basically steal common credentials, like for example the password and shadow file, or some browser vault file, or something else, or wallet files, for example Bitcoin wallets, or so on. Then also we want to be able to start a keylogger on the device and also stop the keylogger on the device again. And how that will work is that it will write to a file, and every time a beacon is sent, the file will be sent as a result in the beacon and then be cleaned again. And when we stop the keylogger, it will be stopped. And this is the updated overview of our C2 communication. As we can see, as a result of the beaconing, we get commands sent, and here we can also fetch results from the C2 server. And then there's also a debate on how we can do our graphical user interface. Either we could have it as a native graphical user interface directly running on the system, and we could also have a web interface, which is very common. But I've decided to go with a native graphical user interface, and the main reason why is because the browser doesn't get into our way. So when we download, for example, files, they can't be blocked by the browser and they can't be scanned by the browser. Also, we have more power, so to speak, that we can easily start new processes, new threads, invoke system commands, and also access the file system directly. So that is also a plus. And most importantly, of course, it looks cooler. So now when we plan to build our graphical user interface, we need to have some idea how that might look like and what functionality that UI might offer. So here we have some examples. For example, here we have poison ivy. Here we can see how the implant is built. We can here set up some things about the connection of the implant, then how it will install, like how to set up the auto run and where to copy the file or where to install it to. Then also, what is interesting here, we have a mutex, so only one process of our implant is running on the system. Then also we can choose the format we want to export to, which is either a portable executable file, or we can also directly export it as a shellcode. So it might be the payload of an exploit, for example, or opens up some other delivery options there. Then we have an overview of all the connections we have with some basic information. And then we have a palette of commands that we can run on the system like that. Of course, we can't easily do all of that in our C2 because this one had a direct TCP connection with to the client, which we don't have. We have a relayed and more sparse connection. So things that require a lot of back and forth might not be easily implementable on our side. So just keep that in mind. But these are some of the information that we have, some of the functionality that we have. This particular E2, which is Poison Ivy, we can capture the webcam and have a screen capture, a keylogger, and so on and so forth, just to give us a rough idea. Then we have another one, which is Bifrost, and we have a very simple GUI here, basically also with a list of connections, and then we have some simple buttons here, and also we have a listener, a TCP listener directly open from that GUI process on the port 81, so that is also a direct TCP connection. And here we also have a builder to customize our implant. Here, what is interesting, that we have a rootkit built into the C2. Looks like that it even has a kernel module that maybe hides the implant. And yep. Then we have another more fancy looking remote administration tool, or C2, and basically has the same rough layout with a command overview and then some basic client information. Then we have a very known remote administration tool called Dark Comet, but the functionality is here also more or less the same, so we can see it diverges a little bit. Also with an implant modification tab where we can customize it to our liking. And this is how a connection will look like. It has a screenshot attached, but other than that, it looks basically the same as we've seen in the previous ones. And then we have probably the most professional command and control framework, which is Cobalt Strike. And it also follows a similar design layout where we have a connections tab, and then, but it has some other stuff up here, and it also has console windows with an event log and also listeners. But there's, of course, many more. For example, we have the first one, which is Sub7. That is very simple, and we have, of course, some other ones. So what we've seen, most of them have an implant builder, and for that we have some takeaways here. So what do we want for our implant? We want to have it modular. We also want to have it persistent on the system, so when it restarts, we also want our implant to start. Then we want to have some functionality for hiding it, so it doesn't get caught too quickly. Then we might want to be able to inject into other processes to read to read their memory, or to access their connections and sockets and so on. And then we might also want to be able to infect other programs. So for example, when we have a direct infection of a program that starts up anyways. We could handle persistence that way, and also it won't get flagged when it's running on the system because it's a well-known program and we just have infected it. Then it should be able to connect to our C2 server and open a reverse shell. So that should not hinder our sending of the beacon and should be done in a separate thread or process. So we could have even multiple shell sessions open. And also it's not blocking, so we can close, for example, also the open shell sessions through an update to the implant or restart them or so on if they get caught up or if they maybe crash or something. We don't want the whole implant to crash. Then we also want to start a keylogger, and that should happen in a similar fashion. That should also spawn up a new thread or process that handles the keylogging. Then we want to be able to execute some built-in commands maybe, and that should be probably the sleep and so on and so forth. Then we want to be able to store the results until they get sent off with the beaconing. So that might happen in memory in a queue, or it might happen in a small database on disk. So depending on how frequent the beacon is, we might want to save it to a database and then send all the results over as soon as the beaconing happens. Or we might save it directly in memory and have a small buffer for that in memory. And then of course we want to be able to send beacon requests to our C2 server to update our C2 server. So to update, we now have a new service that gets spun up by the C2 server for each connection that we open. So let's say in our GUI, we send off the command to open a shell session to our victim. Then we specify on which port and to which victim. So then our C2 server knows, okay, on this port I need to spin up a listener. And so it spins up a process or a thread that listens on that port. And it also sends that command as soon as the beaconing happens in the response to our implant, and that implant then knows, hey, there is a new session, a new reverse shell session that waits for my connection on port so-and-so. So it connects to that and establishes a reverse shell connection here. And the input and the output can be attached to by our attacker PC. So all the input from our attacker will then be forwarded to the input of the shell that's running on the victim PC, and all the output of the shell commands will then be sent to our reverse shell listener and then here be forwarded to our attacker PC. Then of course we also need to have a database on our C2 server to store all the operators, which are the logins for the attacker PCs. And then also we want to store the victims, which is a list of the connections that have been infected. And also we want to have a storage of the commands because they don't get forwarded directly. We want to buffer them in here. So the attacker sends the commands to the C2 server. C2 server stores it in the database. Then whenever the beaconing happens, the C2 server searches for any commands for that particular connection and then sends those off in the reply. Also, we want to keep track of all the open sessions, so all the listeners that are listening here on our C2 server. And also we want to have a database table for logs, so whenever a new victim connects or whenever a beacon was successful and so on and so forth, we just want to have very extensive logging so we know what's going on. And also we want to store the results. They will of course be sent in the beaconing, and then the attacker can fetch any of these resources through the attacker API here. And for that, we plan out a very simple REST API, but of course we need to have a small overview of the database first. So I think that is a very slightly bit simplified, but it is very close to the actual layout that I have built in. So we first have victim templates, which are basically accounts which can be used by infections to log into the victim API. So for example, when we know one got compromised, we can deny the access through that login, but multiple victim templates can have multiple implants using that login. And here we see basically all the information that gets sent in the beacon. So they get stored in our database on the C2 server. And all of these victims can have multiple sessions open. So we know on the C2 server which session belongs to which victim. Then also for each victim, there can be multiple pending commands. And for each command, there can be multiple results. If we think of the keylogger, it gets multiple results per command. And of course, we can also have multiple logs that also belong to a specific victim. And of course, also we need a small database for the operators. So that is basically the equivalent to the victim templates, but for the authentication on the attacker API side. So that also has a username and a password. And also notably here we have a clearance that is not used right now, but we might have some functionality that's only available for administrators and so on. So we have also a clearance. And how do we design our attacker API? Basically from our GUI, we want to have the possibility to interact with all of the resources in a database. So that means mostly the commands, the victims, the operators, the logs, the sessions, and also the results. So for example, I spoke of some things that are only available to administrators. So for example, only an administrator might be able to update the database for operators. So for example, if some other operator forgot their password, then we might want to have a user with a very high clearance to be able to update their password so they can log in again, for example. We also want to be able to get and update and so on the logs, sessions, and results. And all the methods we want to allow is we want to get, for example, all the results from the C2 server. Also, we want to be able to post commands. Also, we want to maybe be able to get a list of all the pending commands. Also, if we have, for example, mistype of a wrong command, we might want to be able to update a pending command. We also would like to be able to, for example, delete. For example, when we know that a victim is no longer active, we might want to be able to delete it, and yeah. And also we might want to be able to partially update something, but I haven't done that yet. And how the endpoints for that will look is we have an API, and then we have the resource, for example, operator, and then we have the identifier, and then depending on the HTTP method that we use, we either retrieve, create, update, or delete the resource. So that is the rough overview, but we will take a look at how that looks practically in the code. Then for the technology, for the client, server, and implant, we all want to have them written in C++, and that is in modern C++ 23. Also, all of them should have a simple database, and I've decided to, for simplicity, always use just SQLite. And on the client side, that is mostly used for configuration. Here on the server side, we've seen the database layout, and here on the implant, we might want to use that for the storage of commands. And here on the implant side, we might want to be able to use that for storage of results and also maybe configuration. No. And for networking, we also always have CPP pawn. And that is my library that I've shown in the last video, and we will utilize that for our networking. And then on the client side, for the builder, I've decided to create a new section in the implant that gets linked to the final binary, and we can modify that using the library elf.io. That is a library for patching elf binaries. And then after that, after we have modified the implant with our current settings, we will also strip it and call UPX on it to pack it. And so that is how the builder works. We're using elf.io to modify an implant binary that is basically serves as a template. And in our custom section, we have all settings for it. There we have, for example, a setting for the default interval. Then we want to be able to set the username and password and also API endpoint. And then also, of course, we want to be able to set the username and password for the victim API. Also, of course, we need to be able to set the server address and also the port where to connect to. Also, we will be able to specify a simple password that will be used to encrypt the settings and also the payloads. So it's not that easy to grab on strings on it, even if we have unpacked it. So, but that is nothing foolproof. That will be just very simply done. That will just be very simple. And then we still need to solve the persistence. I've decided to go with the easiest route, and that is most universal for Linux devices, which is just to register a systemd service. Of course, we could have a cron job. We could also inject into, for example, something that runs on startup, but I've decided against that and just keep it very simple for simplicity. Of course, that already needs to have root privileges so we can register a service. But yeah. Then for stealth, I've decided to act as a browser with our HTTPS connections. So we spoof the user agent and TLS fingerprint to act basically as a Firefox instance. So our beaconing looks like it's coming from a browser. And then we want to be able to rename ourselves to some benign service name. And also we want to have a slight randomization of the sleep intervals between beaconing, between the beacons that were sent. And of course, as we've seen, we will have a stripped and packed binary. So at least the string grab, at least grabbing for strings will not be that easy. And also we will have encrypted payloads, so anything that might look malicious can be encrypted with a simple password. And CPP pawn also has a functionality for process injection. And we could also think about infecting other programs that are already on the system to hide, but I decided against that for now. I might look into that in future videos, but for now I just wanted to get it running. So with all of the planning and theory, now before we do a deep dive into the code, let's just show you how the finished product will look like. We'll have our build directory here, and here we have a client application. And in here we can sign in to our C2 server or start a local server. Here our C2 server will run locally on this port, and these are my login information. And right now you can see that the login failed, and here in the background you can see that we can't connect to the server. So for that we would need to have the server running. So let's start this server here in a new terminal, and let's move this to the side real quick so we can see the terminal better. And here we can see that the attacker API that we've shown on our diagram is now started on this port, and the victim API, REST API, is started on port 3000 right here. And these are the API endpoints for our attacker API. And you can see that the server is now listening. So let's start the server. Right now we can see that we don't have any victims, so we first need to fetch them from the server. And here I have played around a little bit. So we get these entries with some basic information about the victim. And in here we can send commands to it and so on. In this tab we can see a log of all the things that happened. Here the attack are things that happened remotely or are relevant for the attack. And the local log is the client log that is cleared every time we restart the client. So we only see the fetched victims from server here. But as we continue, of course, there will be more stuff added. And this is a scroll view, so you can scroll up and down and so on. And in here, in the settings tab, we can change the client settings. And in here are the builder settings, where we will be able to build our implant. So for demonstration purposes, let's delete our old implant here. We have this one, so let's remove that. So no implant is here anymore. And here we already have the output directory, but we can of course browse. So we can select where we want to put the implant, and we can have login information here. If we change anything here, we need to register the victim user. So the implant can use this login information to call back to the C2 server. But for our settings, let's leave it at that. And here we specify where the victim API can be found, and then we build our implant. Yeah, I don't think I have much logging enabled there, but we can see the implant here. If we do strings on our implant, we should then also be able to see all the settings we've specified here. Let's do it like this. And you can see here, we can see our victim 1. And if we grab for hello, we should also be able to grab our password. As you can see here, here's our password. And of course, for a real implant, we could then of course also strip it and pack it. And then we would have our implant that's ready to be shipped. So now let's send a command to our implant to open a shell. This will then be pushed to the server. From here, let's take a look at the logs. Yeah, this is just a GET request to open a shell on this port. And in here, we can see session was started on this port, and then our operator is now waiting for a victim to connect. And then our victim would need to fetch this command from the server and then connect to the session, and we can then remote control it. So let's like here, debug session. But as we can see, we have established a remote connection. So if we type in ID here, then we can see we got the command, and the output of the command was that. And here on the operator side, we can also see that. And just so you can believe me, we print the working directory, and as it shows here, we are in the implants directory and not in our client directory. So yeah, and if we continue to send commands here, you will also see that this is also a scroll view, but it takes a while to fill up. Yeah, but as you can see, this has a limited buffer, and it will at some point cut off the top part and continue down here. So who am I? Me, and I don't know, you name. And it prints out the information and so on and so forth. But yeah, that's everything I want to show you, just the basic functionality. We can also toggle full screen so we can see a little bit better. And let's see. Yes, that's everything. So let's stop this here and let's take a look at the code at how all of this works. We first of all have some subfolders here. So let's take a look at the CMake directory. In the top level CMake, we just set up the project, set the language standard, and so on. And also we include our CPM to manage our dependencies and download our dependencies. And then we branch off to our source directory. And in here we have common, which is shared code between client, server, and Implant. So all the core functionality is in common, and then client-specific code is in client, server-specific code is in the server directory, and Implant-specific code is in the Implant directory. So let's take a look at the common first. In here we have a logger. This is just logging functionality for the command line, and here a little bit of Unix code. In here we have used a really cool trick for the error code. This is a little bit messy and doesn't work quite as expected yet. So all the code was a little bit rushed, so I can get a minimal viable project or product working here for this video to show off and to show you how it would be put together. And of course this will mature over time when I will continue to work on it sometime. But yeah, this is the cool trick I wanted to show you here with the source location. And we have a default argument here for the current source location. And the interesting thing here to note is that we don't get the source location here of this file, but we get the source location of wherever it is invoked, because it's a default argument, and this gets evaluated as if it was passed in when it was invoked. So that's really cool to know and also very interesting. Then here in the implant config header file, we specify a new section for our builder. If you remember where we built our implant, there we could specify some options, and these will get put into their own section here. So we fill in all of that, and then in our implant, so here it is. Basically this is then in its own section, and this section can then be found in our builder to change the data in here. And these are some default values that we put in. And in the client, in our builder, we can then see that we scan for our own section. Let's see, build implant somewhere in here. We first of all, of course, fill in all the details. Here our new config, there it is. Then we write it to the offset where the config section was found. And in here we scan, is it config section? Here we scan for the config section name, we scan over all of the sections and then check if it's the same name as the config section name. And here we specified the config section name as mxconfig. And yeah, and if we found that, then we get the offset of that config section and then override it at this location here. Yep. So that's everything for the config. Then of course we have some more stuff, especially for the database and for the REST client. I think that is the most interesting thing. So here in the database we have some wrapper for our database and a config and an implementation for that. And that basically just wraps our SQLite database. And then we have an interface for our data objects, and they all need to be serializable with JSON. So that is what we get here. And this is how one data object might look like. It inherits from our templated interface. So we get all the JSON serialization functionality. And then we just specify here our database fields that this table has in the database. And here is how to serialize it with Glaze. And we do that for all of our database tables. And this allows us to have a common interface for these between our client, server, and implant. So in our client, we have a client class that handles all the REST server interactions. As you can see, it is a little bit longer. This is basically how it might look like. We have basic authentication, and we just get our username and the password for the user we are currently logged in. And then we make some request and specify the endpoint. And the REST client already has the server, so we just need to append the endpoint. And as you can see, it's pretty straightforward to use. All the magic here happens in the CPP pawn library in the REST client class. As we can see here, we are now in the CPP pawn library, and here we have a templated function that basically does all the serialization and reading of JSON for us, so we get the correct data type back here already. So much for that. And here in the REST client, yeah, this is just the default REST client that's offered by my CPP pawn library that we covered slightly in the last video. But yeah, so much for that. What else is there to show? Of course, these endpoints need to be specified on the server side. So on the server, we then have an endpoint here. And here I have an endpoints directory, and here we have one beacon endpoint where we just provide the beacon and then get our commands back. And also the beacon might contain all the results of the previous commands that have been run since the last beacon was sent, of course. And as you can see here, the IP, if we specify auto or this IP, then it should be filled in by the server, because we already should know the IP address of the client, but I haven't implemented that yet. So in the client, we still see that auto is filled in there. And here for our attacker API, we have all the resources. Here's some helper functionality. Here are some templated implementations because they are all for the different resources. So I decided to just have a templated version. And in here we register the create, delete, and get. Of course, this design makes it a little bit less flexible because all the resources need to be handled the same way. But this allows us to register endpoints for resources very easily. We just specify this short function here, where we get the manager for the resource and then register an endpoint like this. So it's just one line essentially to register all the endpoints for a resource. And this happens for everything, for the logs, for the results, for the templates. Templates are just logins for victims to log in. I just called them templates because they might contain some other default parameters for this victim in the future. I didn't design that yet, but this was named with that in the back of my head, so I can expand it in the future. And then we of course need to call all of the register functions and pass in the server where they should be registered. And the server just hosts the attacker API, and that is started here in the server. As we can see here, start attacker API. Here we specify get in the port, and then we get in the certificates, and then start the attacker API with this TLS configuration. And if we have a locally run server, then we don't want to use authentication. Otherwise, we want to use our authentication middleware, and that is just basic auth. And I've implemented that very stupidly, but just very simply, reads in the authentication header, then decodes the credentials. When we can see here, we get the authentication header, and then we decode the credentials, and then we split the username and the password, as we can see here, and then we just select the username from the database and check if that username has that password. So as we can see here, through the repository that handles all our database access, we get by the username, the user, and then the auth result is that user we actually found that user because I think we get an optional here, yes. And then we check if that password is actually the password that we got in the basic authentication header. So much for that. Yeah, we have one test endpoint. I just implemented that to see if the server runs at all, so I can easily check that with Postman and see if the endpoint is up and basic authentication is working correctly. And also the open session and closed session endpoints are very easy get endpoints, and we just provide the port as get parameter, which might not be the best idea, but I decided to go the easy route for this first iteration to basically show it off to you. And of course, we can test when we start a server. We then have the option to interact with it using Postman to test all the endpoints. And this is also what I did before I implemented the client and the implant. As you can see here are some other projects of mine, but we have, for example, here the operators and app operator endpoint, and we can get the operators here. So let's send it. And we can see here we have one operator ID is that, and the UID is this, and so on. And we also specify the clearance that might also be used in the future, but not now. And we can also fetch our commands. And as you can see, we have all the commands we sent, and status 2 is completed. So we can see status 1 is sent, and status 0 is pending. So we have a little bit of everything in here. And a lot of them are actually still from testing, so they might just be junk and not be sent to the correct victim, for example, so they might be pending indefinitely. And there's also a really cool plugin for Visual Studio Code, where when we are in the debugging stage of our project, we can then open SQLite databases directly. So if we go into bin, then let's go into client, and then in here we have, for example, the server database, and here we can see all the commands. As you can see, we don't have a valid UID here yet because I didn't implement it at that stage. And in here we mostly send session commands, and you can see the command is very simple. The session means open a session, and then the IP to connect to that hosts the session, which is in our case just the C2 server, but it might be specified as some other server in the future. And then the port, and this is the client that should receive the command, and this is the UID for the command. And here in the config, we just have one entry in the logs. We can see all the attack logs in the database. They can be created. I don't distinguish here yet between logs that have been created by the server or by the client. They all end up here, and they all have a Unix timestamp. And then operators, as we've seen in Postman. And of course, this needs to be hashed in the future, but I didn't do that yet. And then results. We can see the results of commands that we've executed. Right now, we just see the result of our session command. And through this UID, we could link it back to the command that it has been associated with. And sessions, we don't have any running sessions, and also they are not registered in the database yet. Yeah, I didn't do that yet because session management is not complete. So session management is not complete yet. And here, victim templates, we can see that I have registered the same login credential multiple times. that is possible right now. I think I should check in the future if this has been registered yet, so I don't have the same exact login multiple times. And here in victims, we can see here the status gets set to 1 by the beaconing process, and there should be a cron job that I still need to implement that checks the last update and then sets the but I didn't do that yet either. But this plugin is really helpful. Let's see how that plugin is called so you can get it also. Where is it? Yeah, this is the one I'm using, SQLite 3 editor. Found that really useful. So otherwise I'm always using a database program in parallel, and I found this to be much easier to switch around when I'm testing. So much for that. And then, of course, there's the UI that needs a lot of improving, but it looks quite okay for the time I put in. And this, of course, is a lot of spaghetti code. I'm using RayGUI from Raylib here, Raylib RayGUI. And yeah, it's just very easy to get something on the screen. But the code here isn't the cleanest, but it's just, yeah, a lot of spaghetti code to get the client interface. All the functionality of the client is actually specified in the client itself. I've used the singleton pattern here extensively, as you can see here. For example, the client is also a singleton, and we specify the database that it uses locally for its configuration, and that's just client DB. And of course, it's also an SQLite database. On the server side, I'm also just using an SQLite database, as you've seen, just for simplicity. If you want to expand on that on your own, you might want to use another type of database, like, for example, PostgreSQL for all relational data, and then maybe have MongoDB for file storage also, or for other unstructured data, such as results of commands or something like that. But yeah, this is the interface for the client. As you can see, all the functionality of the client is handled through this client singleton. And yeah, that's so much for that. And the implant is relatively straightforward for now. Also, we have a lot of logging currently, but yeah. Here at the very beginning, we check if we have passed an install flag, and if it's an installation, then we install the persistence, which will just copy it to into the systemd services directory and start it. We can take a look at that. It will copy it into here, systemd system, and then we write the service file, and that will be put into our service file path, and that is just the service name dot service. And then at some later stage, we will start the service here, and with that we will have persistence with the enable command here. And yeah, this just makes sure that the enable should, I think, already run the service, but the start command here will then make sure that it is actually started. So, and if we are in this installation, this is everything that happens, and then we return false. And then, of course, in the service, we will enter this without the install prefix. Second here. Of course, this will just return, and then it will enter this again without the install prefix, and then we get the debug statement here starting main logic of the implant. And in here we have some browser impersonation, and I've just chosen to use a Firefox profile here. And in here we have just some browser fingerprint that an actual browser might use. Here by default, I've set it to my own CPP pawn browser, and yeah. And then with this browser configuration, we then create a REST client. Where is it actually passed in? Yeah, here as the config. Yes, exactly. And here we set the path or the URL to our victim API, REST API. That is specified in our implant config. And this uses also SSL and doesn't verify the certificate, so we can actually use our self-signed certificate on the server side. And we also set the basic authentication. This sets the username and password for the victim. And the default sleep is just the waiting time between the beaconing before another beacon is sent. And we get that from the configuration as well. And then our command fetching and beaconing loop starts with a lot of debugging as well. We first send off our beacon. Where is it? Command list. Yeah, exactly here we send our beacon. And then the result of the beacon is the command list. And in that command list, we then check which command we have. Do we have a timeout command? Then we do this. Do we have a screenshot command? Then we do this. Do we have the loot command? Then we do this, and so on. In here, the most interesting one is the session. And here we have our session manager that starts the session. And if we are provided with the close command, then we have the session manager that stops the session. And yeah, this is basically everything we do. And yeah, this one is just for the keylogger. And then we have also a jitter here that's just a random number of seconds. So we don't get detected by some heuristic that automatically detects heartbeats. So this might be just enough to throw them off a little bit on the network analysis side. Of course, this is nowhere near stealth. And here in the beaconing, we can see how that looks like. We basically put together our beacon with the user, then the operating system, and then here the internal and external IP address, then our client UUID. Yeah, this one might be interesting. The client UUID is persistent per client. As we can see in here, I decided to go the very simple route and have an identity.dat file. And in here, we just have this prefix and then GUID. And that identifies the client on the server side. So yeah, it knows which commands to fetch, and the server knows which client has connected. This might be not the best idea. Usually you want to tie it to the hardware it's run on, for example, and hash some hardware ID or something and make it also hard to tamper with. But this is just a very trivial solution that I implemented, but it works for now. And yeah, I think that is already everything. Just let's take a look at how to set it up. If you initially have it checked out. So let's go here. So let's remove our build directory once again, and in here, in the root of our repository, once you have checked it out from GitHub, for example, if you want to compile it yourself, you can take a look at the presets again. And I provided one default preset here, and that will set up the build directory for you. It might take 1 or 2 seconds. And once that is done, we will then have a build directory, as you can see here. And there you can just specify dmake build and then the build directory. And this will also take 1 or 2 seconds. And then once the building is done, we can go into the build bin directory and you can see that we have an implant server and client directory, but all the important stuff is already copied into the client directory. As we can see here, we already have the implant server and client executables here, and there are no database files yet. And the first time you start, you want to copy the server executable wherever you want to run the server. This is mostly on some dedicated server. And the first time you start your server, the installation is very easy. You just start the server executable and it will ask you some questions. For example, which port should the attacker API listen on? I will just provide the standard port here. And where should the victim API listen to? or listen on, and I will also specify the standard port, and it will then generate the server certificates. And then we need to set up at least one operator account or attacker account, and I will just provide something here. And then it gives us feedback that our user has been created, and it asks us if we want to create another user, and we just say N for no, and then it will start the server for us. And if we cancel out of the server, then we will see that some files have been created, notably the server database, then a victim directory and an attacker directory. And in the attacker directory, there is the certificate for the attacker, and in the victim is the certificate for the victim API. And now when we start the server again, it won't ask us for anything again. It will just read our configuration and will start the server for us. And of course, we will then also have the database file with our operators, as we can see here. Now we don't have any victims, of course. And let's close out of our old terminal sessions and let's create a new one. Of course, we can use then our operator data to log in, go here, bin client, and start up our client again. Here we then, of course, need to specify our data. And here we need to specify our local IP or whatever IP our attacker or our C2 server is running on, and then we can log in. And we have some cool about screen here if we click there. But what we can see here, we don't have any victims yet. And for that, we of course need to provide a client, or we build an implant. So let's call this YouTube guy, and the password 777. Yes, just put it in outputs, and the service and so on is fine because we won't install it anyways. Then when we start a new, move this off to the side. When we go into build in client, we will see that we have an outputs directory here. So let's go into outputs, and in here we have an implant file. We forgot one thing, which is to register the victim user. So let's register it. And now when we go to our victim templates, we now have the YouTube guy, and we start our implant. We then should have a victim here, as we can see here. And it should also come up here in our overview of connections. And then we can open a shell on our victim. And we just need to wait for our victim to call back to us to receive a list of commands and to open a reverse shell to us. So let's wait. In the meantime, we can also see that we can have built-in commands here in our shell. And yeah, I just made one command here, but this can be expanded on in the future. So see you in a second when our victim has called back to us. And now, as you can see, our victim has called back to us, and this is the result of the beaconing, and it received one command, and then it executes this command, and the command is session and the session server and the session port, as we can see here. And here it tries to open an interactive session on this port, and then now it sleeps again. So now we have an interactive session. So if we put in ID, for example, we have full administrative control over the victim again, as you can see. I think that's everything I wanted to show you for the code part and for the demonstration part. So here in the browser, I just want to show you that I will publish this C2 framework, of course, on GitHub for you to use under an MIT license. So it's very permissively licensed and you can extend it on your own. And I can't probably make this into something great myself. So any pull requests or commits are highly welcome. And yeah, I will update this README really quickly and publish it after I have published this video. And then another thing I wanted to show you is the C2 matrix. I will probably link this in the video description or on my website. If you can't find it in the video description, I will put it on my website. And here are an overview of other C2 frameworks, and some of them are also open source. So as you can see here with the GitHub link, and it lists also the license. This one is with an MIT license, so it's very permissively licensed. And here you can also filter by language. And yeah, let's take a look at this one. And if you are searching for inspiration, you can also take a look at the code here. This one is written in Python, but if you are familiar with C++, it shouldn't be that difficult to adapt the Python functionality to your C++ C2 framework. And yeah, this looks really cool. I didn't know that before, but for example, there could be a lot to take away from, especially from a UI design standpoint. This looks much better than mine, I think. And then another thing is here on hackforums.net, there's also a little section for hacking tools and remote administration tools. You should really treat this website with caution, because I think it's not the most trustable source of information, but it can also help you to get ideas for your C2 framework. For example, let's take a look at this thread where someone tries to sell their C2 framework or Red or whatever. And also this looks much better than mine. So you can take some UI inspiration from here also and take a look at all the features that this has and so on, and see if you like anything of that. So let's just jump back to the PowerPoint presentation. So with all of that, we've taken a look at the code and at the program, how it looks like when it's done and how it's structured, but we still only scratched the surface. There is a lot more. For example, we could have scripting either on the C2 server to automate responses, or for example, we could have broadcasting of commands. We could also have the ability to upload scripts to the Implant to execute. We could have mutation engines and self-modifying code. Especially in the builder, it would make sense to modify its signature. Then we, of course, could have rootkit and bootkit functionality to hide even better. In the network, we might be able to infect multiple devices. So we might have a Kademlia network, for example, inside of the network that sends all of the results first to a master node and only then sends it out to the wide area network over one specific node. And that also that master node might switch. So it might be one obfuscation method that could be used. Also, we could utilize DNS tunneling for that. Take a look at DNSCat2 on GitHub. Also, we only have a simple implant, but we might want to build droppers or stages that, for example, only have anti-VM built in and so on, and only decode or download our payload when we know it's safe to run. And that might also be more modular in design than what we have now, and might also end with malicious Word documents and so on. Then, of course, we could look at how to utilize exploits to either hide or to infect. Then, of course, our methodology is not very stealthy. The EDR evasion topic is a huge rabbit hole on its own, but we don't have time to cover that here. And also, I'm not an expert in that. What I find is that you just want to blend in as much as possible and only do what other legitimate programs do and to not stand out. That seems to be the most effective strategy for me. Then also, we only have built a Linux implant. We might want to tackle other platforms. So for example, we might also want to tackle Macintosh or Windows. Also, we might want to You might want to explore other C2 channels. There's a whole list of that somewhere. Some C2s operate over well-known services such as Discord or Notion or Slack or so on. So it looks like regular user traffic. And of course, what we also didn't cover for good reason is ransomware functionality that is also built into a lot of C2 frameworks. So with that, we've taken a look at how to build our own C2 framework. I hope you learned a lot from it. And with that, see you in the next video.